Okay, next we're going to look at conservation of momentum as applied to rockets. I'm going to do an example using Kerbal Space Program, and then I'll get into the physics of applying conservation momentum to rockets. So we're going to look at momentum via a rocket. So I've designed this fantastic rocket here. Look at this beauty. It's got an extra rocket on the left, it's got one fin, and we're going to investigate how conservation momentum can be used to understand what's happening here. So let's go. Oh god. Oh god. Oh no. Oh no! Okay. Maybe I'll design it better. Let me see if I can make something a little bit better here. There it is. Okay, so let's fire this sucker. And as it's flying up, right, it's sending fuel downwards at a very high velocity, which is carrying momentum downwards. And so by conservation of momentum, that means the rest of the rocket is gaining momentum upwards. And we want to launch it into orbit. So we're going to start angling it, because if I just go straight up, it's just going to go up for a while and then fall straight down. But I want to put it into orbit. And we'll get into, gravity and orbital mechanics a little bit more. But if I want to get into orbit, I've got to angle it sideways so that it's starting to move around the Earth. And I'm also going to turn it and point it in the direction that the Earth is rotating, or in this case it's Kerbal, not Earth, that it's rotating such that it's moving towards something like an orbit. You see how it's getting so hot there? And the first stage is done, so let me fire the second stage as soon as those things are clear. And now I'm moving outwards. And so let's zoom out, and you can see here a little path predicting the path of the rocket. And that's the apoapsis, the farthest distance, and it's just outside the atmosphere. Right out there is going to be far enough, so I'm going to coast until I get to the end there. So let me fast forward a little bit, and once we get to the farthest point, I'm going to point in the direction that I'm moving and turn on the engine again and try to so let's hit the engine and let's hit go one more time, and we're going to start to accelerate a little bit faster. There, now we're accelerating again, and I'm sending fuel that way, which is giving me momentum that way. And you can see that the path is changing and it's slowly moving. Right now I'm going to hit the ground if I keep going on this path, but if I keep accelerating for long enough, this thing will eventually turn into an orbit. And so this illustrates very well conservation of momentum. Sending momentum, sending fuel with momentum backwards will propel me forwards with more momentum forwards. And there's a beautiful view of the rocket as it's moving around Kerbal. Let's see here. You can see that the apoapsis is slowly moving around and it's turning into an orbit. So look at that. So now we have the whole orbit, and I've achieved orbit. And if I were to just, fast forward this some more, I would just be orbiting around forever and ever and ever. Gravity's pulling me in, but my momentum is carrying me around. Now, if I wanted to, what I could do is point in the opposite direction that I'm moving. So I'm going to turn this rocket and point it against the direction that I'm moving. And what happens is, if I do that and hit the accelerator again, or turn on the rocket, what'll happen is it'll send momentum in the direction I'm moving, which will cause my rocket to slow down. So I am now going to slow down the rocket. So it's almost already pointing in the opposite direction. So there, making some little adjustments. Now I'm pointing retrograde motion, which means against the direction I'm moving. And then I'm going to fire this sucker. All right, so if I hit fire, look what happens. Suddenly the orbit is shrinking because I'm slowing down. And now it looks like I'm going to go and I'm going to hit, if you follow the path, it looks like I'm going to hit something like the South Pole, maybe. So let's, hit fast forward and keep going. You see that I'm slowly losing altitude. If you look at the top, there's my little altimeter, and it's moving down. And I'm just going to get rid of these extra steps of the rocket here because I've got too much stuff here. So I'm going to, this is all for going to other planets. I'm just goofing off with this one. I'm going to now... It's getting hot. Re-entry. If you come in too fast, it gets too hot and you'll burn up. But I think I might survive this one. And the heat shield is taking care of all that heat instead of burning up my little Kerbal. You can see Jebediah down there. He looks pretty unhappy. Oh, he looks okay actually. So as it's going down, fast forward some more, and I deployed the parachute, and it's going to slowly come down and land on, I'm thinking, the South Pole. And so here we know we have different things going on than conservation momentum. Here we have drag. This is different than conservation momentum. We have the air interacting with the parachute and exerting a force, but the takeoff part was conservation momentum, which was kind of an important, which is what I was trying to illustrate there. So now that I've landed, boom, oh, I broke part of my ship again, but it looks like I'm still there. Kerbal is still alive. So now I'm going to go out, explore the South Pole. And that's basically how it works. That's the end of the intro, so now let's look at the physics behind this thing.
Hello, this is Tess. This is only a test.
So let's get into the physics of this thing. Here's a reminder of some of the basics of momentum, right? Momentum is defined as mass times velocity, and we have looked already at conservation of momentum. Momentum initial is equal to momentum final. We're going to use that to describe the motion of rockets. So consider a rocket mass m moving at speed v. This is its initial state, and if it starts to send fuel, turns on its engine, it sends fuel backwards with some speed backwards, then its mass will decrease by a certain amount. We're going to assume dm is a negative number. So it sends dm backwards, and it increases its speed forward by conservation of momentum. So dm sent backwards increases the momentum of the rocket forwards. So the rocket and the exhaust can form like an isolated system, and we can apply conservation of momentum to that. So here you go. Momentum initial equals momentum final. So the momentum initial is just the mass of the rocket times the velocity. And then the momentum final is the momentum backwards of the exhaust plus the momentum forward of the new rocket with some mass loss, right? So this is the rocket, and some this dm is a negative number, so its mass is a little bit less, but it's moving a little bit faster. So the sum of this momentum should be equal to the sum of this momentum. And we're going to simplify a little bit here. We're going to write the velocity of the rocket relative to the frame, all right, which is v plus dv, is equal to the velocity of the rocket relative to the product, so how fast this rocket is moving relative to the stuff coming out of it, plus the velocity of the products relative to the frame. All right, so velocity of the new velocity of the rocket is equal to the velocity between the two plus the velocity of the product relative to the frame. That just lets us rewrite u in terms of the final velocity of the rocket minus the relative velocity between the two of them. And that's going to help us with our calculations. So there's that expression again, right? If we substitute that into our conservation of momentum equation that we had, so we're going to plug the u right into here and simplify a little bit. And we get, after we simplify, we get this equation here. Minus dm v relative equals m dv. If we divide both sides by dt, we get this. Now, dm dt is just the rate at which the rocket's mass is changing. So it's how fast the rocket's mass is changing. We're going to set that equal to minus r. That's going to be our expression for the rate at which the rocket's speed is changing. And dv dt, of course, is just acceleration. So it'll be the acceleration of the rocket. So this gives us the first rocket equation, which just tells us that the acceleration can be figured out at any given moment if you know the relative speed between the rocket and the exhaust. Remember, that's how fast the stuff coming out the back is going relative to the rocket, times the rate at which it's expelling fuel. So you can use this to calculate the acceleration. And here's the thing, right? This whole thing is so different because we can't use our usual kinematics equations because the mass is changing with respect to time. That's not a normal thing for objects in our other equations. When we use P equals mv, we usually assume m is pretty constant, but here the mass is constantly shrinking for the rocket, and it makes it a much more complicated problem. So this is one situation where we can calculate the acceleration at any given moment. But the acceleration changes every instant because the mass is constantly going down. We can get a second equation. We can get a second equation, all right? So let's move one step back before we divide it by dt. If we solve this for dv, okay, and we have minus v rel dm over m, and we integrate both sides. So this side we're going to integrate it between the initial speed and the final speed, and the right side we're going to integrate it between the initial mass and the final mass. And so this gives us the second rocket equation, which tells us we can calculate the change in velocity. It's going to be equal to, it's going to depend on the relative speed between the rocket and the exhaust times the natural logarithm of m initial over m final. So this is going to help us calculate the speed of the rocket if we know how much its mass changed by. So let's do some sort of examples of this. What is the initial acceleration of a toy rocket with a mass 1 kilogram that ejects exhaust at a rate of 100 grams per second with a relative speed of 200 meters per second? So let's just say here's the ground, right? And we have, you're standing here and you just fired your toy rocket, and it's firing exhaust backwards, right? So the rocket's so at the moment, initially, the mass is 1 kilogram, and its exhaust rate, so how fast it's firing out gas, is 100 grams per second, or 0.100 kilograms per second, and it's firing it out at a speed of v relative of 200 meters per second. So we want to know what is the acceleration. So we just use our equation, right? We just use our equation, r v relative equals mass times acceleration. So the acceleration is equal to r v relative over the mass. So 0.100 kilograms per second times, so that's r times v relative, which is 200 meters per second, and divided by 1 kilogram. And you notice the kilograms cancel out. We end up with meters per second squared, which is acceleration, and we end up with 20 meters per second squared. So that would be the acceleration provided by the rocket at this point. That's just the acceleration by the rocket. If we were to also include gravity, right? So our acceleration due to the rocket is 20 meters per second. The acceleration due to gravity would be 9.8 in the opposite direction. So that's going to be enough to overcome gravity. Another example. We have a 600 kilogram rocket that's moving at 105 meters per second, and it ejects 100 kilograms of exhaust at a speed of 250 meters per second. What is the final velocity of the rocket? So so this thing here is 600 kilograms, right? So this is initial, right? And it is moving at an initial speed of 105 meters per second. So final, it has ejected a total of, we're just going to say here, 250 kilograms, no, it's not 250, it's 100 kilograms of fuel, right? Backwards, and its speed relative to us is 250 meters per second. And if we ejected 100 kilograms, what's the new mass of the rocket? Well, it's going to be 600 minus 100, so it's going to be 6,000 minus 100, so it's going to be 5,900 kilograms. We want to find what V final is going to be, right? And so this speed, and so let's write down everything we know. So V relative is given as 250 meters per second. V initial is 105 meters per second. V final is unknown. Mass initial is 6,000 kilograms. And mass final is 6,000 minus the ejected fuel, so 5,900 kilograms. So we can use all that to calculate the V final. So V final, using this equation here, is going to be equal to V initial plus V relative times the natural logarithm of M initial over M final. So V initial is 105, I'll put in units at the end, plus V relative is 250, and then it's the natural logarithm of initial minus final, right? So of 6,000 kilograms divided by 59 kilograms. And that gives us a final speed of, let me do the calculation real quick. So 105 plus 250 times natural logarithm of 6,000 divided by 5,900. And, oops, 250. And that gives me a final speed of 109 approximately meters per second. Let me make sure I got all that right. Doesn't seem like a very big amount. But, yeah. So it started at 105 meters per second and ended up at 109 meters per second. So that's the acceleration, or that's the change in speed of that rocket. One last problem. Let's look at a 1 million kilogram interstellar starship. It's at rest, and it fires its engines just that it ejects fuel at 1 kilogram per second, and it does it for 2 days. So it fires its engines for 2 days, ejecting 1 kilogram per second, and 2 days is about that many seconds, with a relative speed of 1,000 meters per second. Okay, so let's look at a couple things here. We're going to figure out what was the acceleration at the beginning, what's the acceleration after 2 days, and how fast is it moving after 2 days. First, let's write down all our knowns. We have our initial mass is given as 1 million kilograms, or times 10 to the 6 kilograms. We're given that it's firing at 1 kilogram per second. That's how much fuel it's spending per second. V relative is given as 1,000 meters per second. And it's the amount of time that it's firing for is 2 days, right? We can find M final from this easily, right? M final is just going to be M initial minus how much fuel is used up in 2 days. So it'll be the firing rate times the amount of time. Oh, and by the way, 2 days, of course, I said is 172,800 seconds. So when I calculate M final, I get approximately 827,200 kilograms. So it's lost about, roughly 17% of its mass after firing for 2 days. So at least 17% of that rocket was fuel to spend, and that's usually more than that. Usually a large percentage of a rocket is fuel. It takes a lot of fuel to get these suckers going. So we have everything we need. Let's look at A. What is the initial acceleration? So we're going to use equation 1 here. Solve the equation 1 for the acceleration. So the acceleration initial is going to be r, the rate at which we're spending it, times v relative divided by the initial mass, right? Which is, when you plug in everything, r is 1, m is 1,000,000, v relative is 1,000. We get that the initial acceleration is about 0.00100 meters per second. So it's not a very large acceleration. I mean, this is a 1 million kilogram starship, so it's going to take a while to get it going. A final will be the acceleration at the end. So let's think about that. If we are accelerating with the same exhaust speed and the same rate, everything is the same except M final is going to be a smaller number, and that makes sense. We're sort of accelerating. We're putting out the same amount of fuel, but there's less mass that you're pushing. So the acceleration will be faster and faster as more and more fuel is spent. And when we do this, we see that the acceleration goes up to about 121 meters per second. So acceleration has gone up after 2 days. If I wanted to calculate how fast it's moving, right? V final, we're going to use equation 2 here, right? V final is equal to V initial plus V relative times the natural logarithm of M initial over M final. And when we calculate that number, we get that after 2 days of burning, it's approximately 190 meters per second that it's accelerating at. Rockets are fun.